All right, so I guess I can start. Hey everyone, my name is Markus Dregi, and I'm here to talk about uncertain models and how we can utilize them to learn from the past and optimize for the future. Now, the scenario that we have at hand is that we have a model on our computer that tries to model something in the real world. And what we can do with this model is that we can simulate. Now, what do we want to use these simulations for? Well, we want to say something about how the real world behaves today, maybe how it behaves in the future, or possibly how it would change if we are interacting with it. What you can very often see in these situations is that what you're simulating doesn't exactly match what you're observing in reality. There is a mismatch. And this might come from you not having full knowledge of the state of what you're simulating. Maybe you don't have full knowledge about how it is actually behaving, or maybe it's something else. And this is what I'm referring to as uncertain models. We have some uncertainty in what we're simulating. Now, we faced these kind of challenges many places in Equinor. One of them being reservoir models, because no one really went down and looked at these things, right? I mean, they're several thousand meters below sea level. So what we do instead is that we get seismic data, we look at rock properties, we do drilling samples, and then we have domain experts that build these models as good as they can. But of course, there is some uncertainty in this process. Another place where we face the same kind of challenges is when we're building offshore wind farms. Because also here, we're setting up wind farms under new weather conditions, possibly with a new layout, possibly with windmills that isn't exactly as the ones that we have used before, and possibly with a slightly different operational scheme with respect to current wind direction and so forth. And in both of these scenarios, it might very well be that the model that we are simulating on our computer doesn't exactly match what we are observing in reality. And this is what me and my team is developing software for in Equinor. So we are working on a daily basis with these kind of problems. Now, what we want to do is that we want to embrace the uncertainty in the model and say that, yes, we do have some uncertainty. We don't really know what it is like, but we have some clues. And based on this, we want to feed it into some optimization tool and do some robust optimization with respect to this uncertainty. Then afterwards, we get some strategy, and we want to carry out that strategy. And when you're carrying out this strategy, you're actually interacting with this system, right? So you're gaining more data. So now you have more knowledge about the system that you had to begin with. So now you would like to utilize that knowledge. So then we feed it into a model updating tool. And what we hope to get out again is a model which better fits what we're actually seeing in reality. And now, if we have a better model, then why not base our future decisions on that better model instead, right? And then you basically end up in a loop. So now you can find a new strategy, you can execute that, you get more data, you can update your model according to the new data, then make a new strategy, and so it goes. And this is basically the overall scheme of what I'm going to talk to you about today. However, before we go into these complex models with reservoirs or windmill farms or whatnot, I want to talk a little bit about a very, very simple example. Because simple examples, they are always nice. And not only do I want to talk about a simple example, I also want to use a simpler algorithm. And then we are to see where that simple algorithm fails. We'll try to mitigate, and then you'll actually see how we deal with these more complex models, and then we'll go back to the reservoirs and the wind farms in the end. So, the very simple example that we are going to work with is that we have a train, and it's moving along a straight line of tracks. And not only that, but it moves at constant speed 5 meters per second. So, I mean, this is a perfect toy example, right? It's not a very fast train, but it's a good toy example. And what we want to figure out is where the train is along these tracks, right? Now, we don't really know currently, but what we can do is that we can do GPS measurements to try to figure out where the train is. And we do this every second, say. So we get the measurement here. Yeah, we believe the train is over here. A new one, a new one, a new one, and so forth. Now, some of you might know that a single GPS measurement isn't really exact. It comes with some error. And you can already see this in these points because I already claimed that the train was moving at perfectly constant 5 meters per second, and I'm measuring every second, and even though these are not spread evenly out with even distance in between, right? So something there is already off. So what happens is that there is actually some error in this measurement. And I'll use these faded boxes to represent errors whenever I'm doing figures. So the darker parts of it means higher probability, and the whiter ones means less likely. And now the question is that, okay, so after 5 seconds, we have measured the train to be somewhat over there. And that's all good if the error of that measurement is good enough for you. But the question is really, is it? And if not, have we utilized all of the knowledge that we have available? And the answer to that question is no. Because we also know that the train is moving at 5 meters per second. So if we then just go back, what we actually know now is that based on our observation of the train being here after 1 second, we also actually have an estimate of where we expect it to be 1 second later, because we know that it's moving at 5 meters per second. So actually 1 second later, based on this measurement, I actually expect the train to be over here. And not only that, but I also expect, or I'm as certain about that as I was about this measurement to begin with, because we are in a toy example where this train is moving at exactly 5 meters per second always. So now when I get this new measurement of where the train is, I have this measurement, but I also have this forecasted value based on my previous measurement. So now I have 2 data points to base my estimate of where the train actually is. And if you look very hard on these faded boxes, you'll see that they are of equal size. So I'm actually as certain about both of these. And based on that, by intuition, I would assume that maybe the most likely place of this train is actually somewhere in the middle. So my new estimate of the train's position is actually this red dot. And not only that, but this new estimate, the red one, is based on 2 measurements. So I'm actually feeling more confident about that one than I was about this measurement alone or this measurement alone. So I'm actually decreasing the error also of this measurement. And then once again, I can forecast this value. 1 second later, I expect the train to be somewhat here. I can combine it with a new measurement, get a new estimate of the train's position, and that's how it goes. Now, some of you might have seen this before. The mathematical framework that describes this kind of process is called Kalman filters and came in the 60s. It's utilized in signal processing, robotics. It's also utilized for GPS location because the measurements are actually not without error. And we also use a variant of them on our uncertain models because we want to get as much knowledge about this system based on our measurements as possible. But we'll get back to the more complex ones. So what the Kalman filter gives us is an equation to give this new estimate of the train, position of the train, and also an equation to compute the new error of this estimate. Now, these are not the general Kalman filter equations, and that's not the point. I mean, the thing is that I've just removed all of the matrices and vectors and so forth because we only have a single measurement, the train moving along a one-dimensional track. So that's all good. But always, when I see equations, I want to just play around with them a bit and see if they actually match my intuition of what's going on here. So let's just first quickly cover what's going on here. So xk, that's our new estimate of the train position, and that is based on our forecasted value, this one, and our observation being this one, and then some constant factors based on our errors. And then the error is based on the forecasted error being this one combined with the error of the observation. It isn't that important. But let's have some fun with these equations and see if they behave as I at least want them to behave. I'm always happy when my intuition and math, if not originally agrees, then at least in the end agrees. So as you can see, our new position is basically a combination of our forecasted value and our observation. So let's say that I am as certain about my forecasted value as I am about the new measurement. I am equally confident about these two measurements. Then where would I like my new estimate of the train's position to be? Well, I would like it to be in the middle, right? And this is what happens if you plug this in, right? Then you have like two terms of the same size underneath the fraction and one term of that size above, so you get 0.5 both of them, and you get the mean of your forecast and your new measurement. A different scenario would be if you are much, much more confident about your forecast than what you were about your new observation. So maybe you have had this system running for a long time, getting new measurements, being more and more confident about your actual forecast, and then you get a new measurement which has much higher error than what your current forecast is. So then I would expect the new measurement to not really that much affect my current forecast, right? And that's also actually what happens. If this is very big and this is very small compared to it, then this becomes almost 1 and this becomes almost 0, and you basically end up with more or less your forecasted value. So once again, the equations agree with my intuition, and at least I am happy. And how about if you, of course, this never happens in reality, but say that you make a measurement and you have absolutely no error. You're super confident this is exactly how it is. Then you should basically just take the measurement, right? Because you're absolutely confident that that is the right answer. And this is what the equations give you as well. So then, since this is 0, then this term ends up being 0. And this is 0, so this becomes 1. And it's all good. Once again, fits with the intuition. Now we can play around a bit with this estimate of the new uncertainty as well. If they're equal, we get half the variance we had before. If our forecasted error is much lower than the new measurement that you get, so you're much more confident about your forecasted value than what you are about your new measurement, then you don't really gain that much knowledge, right? So you're not expecting your error to decrease very much. And once again, this is what the equations give us. All right. So let's try to apply this kind of math on our train example and see if it actually works. So we are to apply these equations on this scenario where we have some estimate, we do a forecast, we combine it with an observation, and we get the new estimate of the train's position. Now, if you have been waiting for the slide when the equations go away, then this is your slide. They are gone. You're safe. What we're going to do now is that we're just going to talk a little bit about the numbers appearing and see if they make sense to us and see what we end up with in the end after 5 measurements being introduced. All right. So we have to start out with something. So my first estimate is just the train being at position 0, meaning all the way to the left. But I really have no clue. So I just put my error margin to be 10 to the 10 because I don't know what I'm talking about at all. This basically means I have no knowledge. I'm clueless. But still, 1 second later, I know that my train is moving at 5 meters per second. So still my new estimate, my new forecasted value of the train's position is 5. But I have no confidence in this estimate, but it's still my estimate. Now I do a real measurement, and I get back that my train's position is actually 3.58. And let's just say that all of our measurements has a variance of 1, all right? Then what I get back from the equations is basically this measurement because I had no confidence in my forecasted value. And I also did my new variance is more or less basically the variance of the measurement, because I had no confidence in my forecasted value. Then I repeat this process. Once again, the next second, I believe that the train is 5 meters further down the tracks. So my expected position of the train is 8.58. And now I have a variance of 0.999. Make a new measurement, 9.73, variance of 1. And now observe that I am basically as confident about this forecasted value as I am about my new measurement. So if you remember from our previous playing around with equations, we would now actually expect this train position estimate to come out as something right in the middle of them. And that's what happens. And also I'm gaining now more confidence in this measurement. Same thing again. Add 5, same error, get a new measurement, 15.09, apply the equations again, end up with 14.47, and so it goes. All right? Now, if we go all the way back to where we just neglected the speed of the train, and we were just looking at the observations that we made, then in this scenario, we would, after 5 seconds, believe that our train was at position 24.37 with a variance of 1. However, after applying the Kalman filter on all of our observations, we actually believe that the train is at position 25.0035. So that's, I mean, it's a different answer, that's fine. But we've also gained quite a bit of knowledge about this system. We are much more confident about this estimate than what we are about this measurement alone. And you could continue this process and gain more and more confidence. And actually these numbers here, they are sampled from a train on my computer, of course, starting at position 0, moving 5 meters per second, and then uniformly randomly. And then with a standard distribution sampled around that position to get some error into these measurements. So this actually fits very nicely with the theoretical model that I based these observations on top of. All right. But enough with the trains. I mean, that's not why we're really here. We have other companies to deal with trains. So we want to deal with reservoirs, and we want to deal with offshore windmill farms. And these are also dynamic systems changing over time, so why can't I just do this thing with the full equations, with supporting multiple inputs and multiple outputs, and then all should be good? Well, the problem is that I can't actually do this. I'm not able to do that forecasting. And the reason for that is that my simulation model isn't linear. So I can't take my original estimate of the position of the train in the scenario of a windmill farm or a reservoir model and bring it into the future and immediately get estimates of expected value and error of these these values. So I'm a bit lost. And because I lose this, then I lose all of these terms in equations as well. So I mean, I can't use them. I'm lost. So then we have to do something else. But we still want to gain this knowledge as our system is changing and as we get more data. All right. So I said we were done with the trains, but we're actually not. Now we're moving back to the trains. But let's assume now that we don't have a linear model or that we can't forecast it as we did. So we'll try to do something else instead and see how that goes. All right. So what we have is our current estimate of the train's position and some error tied to that measurement. Now, another thing that I haven't talked much about is these assumptions about probability distributions and so forth in these Kalman filters. But what this basically gives you is a probability distribution of where the train is actually positioned. And when I have a probability distribution, then I can start sample numbers from that distribution. So it could be that the train is at this red dot here. Could also be that it's here, could be here, could be there, or it could be any of these places. I don't know. But if we sample from the distribution that we have available, then we will get more samples from the places that are more likely and less samples from the places that are not as likely. So these will be representative of the error that we actually have. And the nice thing now is that these red points here, they don't represent a measurement with some error and something, an uncertain kind of entity. Instead, it represents a very concrete position of the train. Or, in the more complex models, a very concrete reservoir model, or a very concrete wind farm model. So then, we can use our simulators. I can take a specific point here, specific model, and I can simulate that one. Of course, our train simulator is super easy, right? It's just add 5. So that I can definitely do. So I can continue doing that. And then I get something like this. So now, I couldn't bring my estimate and error distributions into the future, but I could still sample from it and then bring all of those samples into the future. That my simulator is capable of doing. Now, this is what we refer to as an ensemble of models. Now, based on this forecasted ensemble, now I have samples of something, right? So then I can actually reason about these samples. So I can say something about what I think that the mean is. I can also say something about what I think the variance of this is. And based on that, if I now bring up again my equations with all of these red terms, I can actually compute these things, and I can get moving again. So by accepting that we can't really reason about uncertainty in complex models, and instead just sample concrete models that we can simulate, we can circumvent this entire problem. And this is called the ensemble Kalman Filter algorithm. Was introduced in the beginning of the 90s. I've seen applications in meteorology, oceanography, and also in reservoir engineering. So it's been used. The author of this actually worked in Equinor for quite a bit of years. He's currently in Norse doing research, still improving these algorithms. Yes, because based on this, I can now actually estimate these things, bring in a new observation, and then continue the computational stuff. And now, I can do this with the windmills and the reservoirs as well. I can take a concrete model of a reservoir, and I can simulate it into the future, and then I can reason about means and errors in the future. Now, there are also other problems that you come into when you're doing these kind of things. So I mean, in this train scheme of ours, we're changing the model as we move along, right? I mean, 1 second down, we actually do a reset, we get a new observation, we change the position of the train a bit, and then we continue further on. Not all physical simulators are so happy about you doing this. Imagine that you're simulating something a little bit, then you stop it, and then you say, yeah, I'm just going to play around with your internal state and change all of the things that you think you know about the physical world, and then you'll just have to deal with it. Then occasionally simulators say, well, this is not really something physical at all, so yeah, I don't know what to do. So what we actually had to do is that instead of introducing them gradually and adopting the model over time, what we actually end up with doing is simulating all the way to the end and then doing a single update step, introducing all of the observations at the same time. Now this is good because you don't have to do all of this crazy stuff with the simulators, which has both problems for the simulator itself, but it also becomes a bit numerically unstable. But another reason to do this, yeah, and it also gets numerically unstable, sorry. But the bad thing about it is that now we only do a single update step. So this is what is referred to as the ensemble smoother algorithm. Now what people have done on top of that again is then building iterative algorithms, smoothly introducing, for instance, observations into the process so that you actually get multiple iterations and the fitness of the model converging over time, because this is much more numerically stable and it also works better in practice. So of course, when you introduce these this sampling or the ensembles of models, that still works in theory if you sample your model big enough or the ensemble big enough and you still have a linear model. But for these complex models, like the reservoir models, you can't really prove mathematically that it works. But you can show with case studies that it actually gives value. Yes. So the main takeaway message from this first part is that if you have a complex model and you want to reason about the uncertainty in it, and you don't know how to do it, then just sample. Get an ensemble of models and play around with that instead, because then you can treat every one of them by themselves, and you have a concrete model of the world, and that you can simulate and just deal with that this is the one and only truth, and then you can reason about the statistics on top of that again afterwards. Now, let's go a little bit. So now we're actually leaving the training samples. We're not getting back to the trains. Let's look a bit about how. Let's have a look at how we can implement this for these more complex models. So, what you start out with. So I'll just use the reservoir models as an example case. What you start out with is a model of the reservoir, and what you want to do is to make wells and get stuff up. And what you have at hand is a simulator, and you have some domain expert that is very good at designing wells, sets up some wells, feeds it his master plan into the simulator. He gets some quality of that plan back again, and then back in the days you would be good to go. Now you can iterate on top of this by introducing an optimizer and then feeding the initial plan of the domain expert into the optimizer, doing optimization with the simulator, and then instead of using the quality of the initial plan as your baseline, you're using the quality of the suggested plan by the optimizer. And really this is not just a simulator anymore, because what you're really getting is like numbers from the optimizer, right? Controlling what you're doing with the model. So you need to take these raw numbers from the optimization tool and turn that into how the wells are to be, which order they are to be drilled in, how much pressure you're going to have here compared to here, and then try to adjust the flow. But what's missing from this picture is the ensembles, right? And there is no uncertainty. So we need to embrace the uncertainty. And we don't know the volumes of the reservoir. We don't really know what it looks like. And typically also you have in a reservoir you might have some water below, and then you might have some oil or gas on top. And you do really care about whether it's the water or the stuff above that comes up, because one gives you money and the other one does not. But you're uncertain about this as well. And you're also uncertain about how these liquids are moving, how easily they can flow, and so forth. So you have a lot of uncertainty in your model. And as we've seen, our solution to this is ensembles. So now instead of simulating a single model and not taking the uncertainty into account at all, we're going to simulate a full ensemble. And now you might be thinking, yeah, that's nice, and then you can do the average or some kind of function on top of all of these ensemble members, and you can use that as your objective function, blah, 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 blah. Not very interesting from an optimization perspective. But what is actually quite cool is that all of these models that you have sampled, they are from some probability distribution, right? So they are correlated. They come from the same uncertain mother model. So you can actually reason about this. So say, for instance, that you're doing local optimization and you are to compute a gradient. Then you have some point and you want to perturb that point and compute the function values around you. Now, the normal way to do this is to perturb, compute the function values of each of these points around you, and then use those evaluations to compute the gradient again. But now you actually know that these different models that you have sampled, they are correlated. So assuming that your ensemble is big enough, what you can actually do now is, instead of taking one perturbation and evaluate that on all of your ensemble, you can take that perturbation, assign it to a single ensemble member, and evaluate that one there. Then you can take another perturbation and evaluate that in another ensemble member, and so forth. And if your ensemble is big enough, this actually works out. And instead of computing, when you are computing a gradient, the size of your ensemble times the number of perturbations that you do to compute your gradient, you now end up with only doing as many simulations as the size of either your ensemble, or possibly, if you want to perturb more than that, the number of perturbations that you want to do. So this actually limits and helps out with the computational resources that are necessary. And I mean, these might be simulations that go on for days, and then you want to iterate on top of that. So I mean, you really do care about this. All right, but now we've optimized, we have a strategy, we get some production data, and then we want to learn from this, right? So we want to take the data that we're getting from production, we want to compare that, as we have seen in the training example, with the simulation data that we get from all of our ensemble members, and then we want to be a bit clever and do something about it. So what we do is that we take this initial model, we feed it into this tool that we call 8. It's an open source tool, and I'll get back to that later on. We compute this ensemble and simulate it. And remember that each of these ensemble members, they are now a very concrete model sampled from our uncertain model. And we can simulate those, and then we can take the values from here and we can compare it with what we are actually observing. Yes. So we do have uncertainty, and the hope is that by getting more data, we can get a better model that better describes the reality. That is really the goal of that process. And we're using these ensemble Kalman filters to gain that. Now, let's just do a little divergence and talk about what we are observing, because I think this is a bit cool, to be honest. So in the reservoir-specific setting, of course, we get production data, right? I mean, you push something down, you get some stuff up, and we measure it. We can compare it to our simulation data, and that's all good. But we also do other stuff. So among others, we put devices on the seabed that can measure the gravitational field above the reservoir, and we can actually detect gravitational changes as we are pushing down something like water and getting something else up. And then what we can do is that when we're simulating the reservoir, then we can first simulate how the reservoir is, and then afterwards we could simulate what these gravitational changes should be, and then we can compare the gravitational changes that we see in the simulation with the gravitational changes that we actually observe on the seabed, and then we can use that data to improve our model. We also do the same with seismic data, so we collect new seismic data by having these boats with these long things behind them. We get more seismic data, and again we can do the same procedure. We get more seismic data, we simulate the reservoir, we simulate how we would expect the seismic data to be on that simulated reservoir model, and now we can compare the simulated seismic data to the observed seismic data. And in this kind of manner, you can try to collect more information than really just production data, for instance, to really try to improve your model, because we want it to be as good as possible. Yes. So basically, just to repeat myself, what we have is that we have some, to begin with, uncertain model And it is important to notice that while in the train example we just said, yeah, position 0, no idea, we really want our prior knowledge to be good, right? So we do spend a lot of time doing these initial investigations, having domain experts and so forth, because we do care about our initial model. So this is much better than 0, 10 to the 10. And we want to feed it into the optimizer. We want to do clever stuff with our optimization algorithms because we have an ensemble. Then we get more data. We want to feed it into our optimization, our model updating tool. Hopefully we get a better model out again. And then in the end, we want to feed that better model into the optimization tool again. And so it goes. Yes, so both this optimization tool and this ART tool is something that our team is working on. That's our project. It's a lot of fun. And this ART tool in particular is actually open source, and you can find it on GitHub. I'll show you the link later on. It's been used by NORS, which is this union of research foundations on the western part. It's also used in the Netherlands by some organizations, and we utilize it a lot. Yes. So we have talked now about these reservoirs, right? And reservoir models. That's what we used in our example. So what do we use them for in the windmill farm setting? Well, so one of the things that we have been studying is different kind of turbulence models behind the windmills, because when you have turbulence and the wind direction goes in the wrong direction, right? And that turbulence will hit some other windmill, and then you get less production from that one. So what we've been using after currently is to try to get a better model for this turbulence, so that we can use that better turbulence model in the future, both to do better controlling of the windmills, but also maybe to get better layouts for future windmill farms. And I think it's quite cool that you can take something, because the reservoir model is just treated as a black box in these tools. So I think it's quite cool that because to be honest, we funded these projects to do this, and it started many years ago. But now when we start to operate also in new domains, we can actually take some of these tools and then just apply them in that setting as well. And I think that's a lot of fun, actually. Yes. And that's basically what I had to say. You can find this ART repository if you want to have a look at Equinor/ART on GitHub. And yeah, thank you for listening. Any questions? Yeah, shoot.
Yeah, I'm trying to understand that. I'm not so familiar with exactly this kind of things. The optimizer, is that the one that will adjust your model to better fit what you're actually observing, or was that another part?
No, so that's this model updating tool. So what the optimizer is doing is taking the uncertain model and making a plan for what you want to do. So for instance, how you want to operate the field, like which wells you want to drill, how much pressure you want to allow in these wells. So because by this you can control the flow in the reservoir, when you want to drill them, etc. Or in the windmill setting, where you want to put the windmills, how you want to react to different wind directions and so forth. So the optimizer is for finding a good strategy to operate the thing that you're modeling.
And the model update, what sort of algorithms are they typically using for updating?
And then it's this ART tool, right? So that is doing the model update, and there, as you say, the goal is to go from a model that has some initial uncertainty together with things that we have observed, and then get a better description out again. And that is using this ensemble Kalman filter algorithms that we saw in the beginning of the presentation. So that's this thing of having this uncertain model, sampling multiple models, then simulating all of those into the future, comparing that simulation data with what we are observing, and then using these Kalman filter equations that we saw used on the train example, but the full ones, and then get a better estimate of these parameters. Yeah.
If you're familiar with Monte Carlo, then that's...
Yeah. Yeah. All right. Thank you for attending.